who can't make it. I am new to using Microsoft Teams. It's the easiest one to use. I don't see a chat box anywhere. Oh, here we go. Let's see. All right. Don't see anything in the chat. Before I get started, did anyone want to ask me a specific question, or should I just start going over stuff? What do you all want to do? We'll be able to review exam 2 on Moodle. Let me see. Will the exam be formatted the same way as the others? Yes, the exam will be formatted the same way as the others. Did I let y'all review the first exam on Moodle?
I don't think so. Oh, I'm wrong. Angela says yes.
Let me check on Moodle real quick. Let's see. Apparently, I have the first exam for sure. I'll set this, check the second one. I'm sure you're right, but I just want to review options. Okay. Just want everything to be consistent here. All right, I just set the second quiz to be reviewable. Still 2 attempts, yes. And let me make sure it is definitely 2 attempts. Just want to be absolutely sure. Yes, attempts allowed 2. All right. This is a cumulative exam. The exam is opening tomorrow morning Central Time, first thing in the morning. I feel like I'm constantly checking Moodle. I'm glad you asked that. It was supposed to be opening October 6th. October 6th at 0 hour. And it's supposed to be closing on October 9th at midnight. And had you not asked about that, I would have been getting a lot of angry messages because it's not how it was set. So I'm glad we had this this video review. Is it a cumulative exam? Yeah, you can't really help but make it cumulative because everything kind of depends on you knowing the earlier stuff. So yes, it is cumulative and opening tomorrow. All right. Did anyone have any other questions about material? I could just start going over it.
The chi-square stuff is going to be on the final exam, right?
Yes, chi-square.
Yeah.
Yeah.
Well, the two forum weird theory things that we had to learn, like bootstrapping and the last one, Bayesian, will that be on the exam? Okay.
They will not. No bootstrapping, no Bayes. But chi-square and Fisher's exact test are fair game because, and the way it'll probably be asked is I'll give you a research scenario and ask what test would be appropriate to use, a t-test, a correlation, or a chi-square. And a correlation is for when there's two continuous variables and you want to know if they correlate with each other. A t-test, or if it's an independent samples t-test, is for whenever there's two sample means. It can be tricky. This does trick people up with the chi-square and Fisher's exact test. Is you don't really have a mean, you just have category members. Like, the classic example is how many people are convicted versus exonerated as a function of whether they're male or female, or white or non-white. And chi-square can answer questions about whether there's any over-representation or under-representation. Like, do women tend to get more lenient sentences, like disproportionately compared to men? Chi-square is suited for answering that kind of question. All right, did anybody have any other questions? No? Okay. Well, I can just start going over stuff, and if you want to stop me and ask me questions, I can do that. I'm just looking for my little review thingy. Where did I put that? I think this is it right here, what I'm looking for. Actually, maybe not. Okay. Let me take a look at the final itself. Maybe that'll help. Yes, there's 20 questions. They're 5 points apiece. Let's see. I'm looking at the exam. It's a lot of application questions. Specifically, like if I give you a scenario, can you tell me if you should be using a t-test ANOVA correlation chi-square? It's a lot of pattern matching in that sense. So for instance, if let me write. If I say, I want to know if students in my stats class, if they're in early morning section of the class versus a late afternoon section of the class, like 8 a.m. versus 3 p.m. class, who tends to do better? Would that be a correlation, an ANOVA, a t-test? A lot of the questions on this exam come down to identifying which test goes with which question. So if I'm asking if it's who has a better average test score in the morning versus the afternoon, you should notice that that's 2 sample means. And when you compare 2 sample means, that's a t-test. And some of the questions might get at the crucial difference between an independent samples t-test and a repeated measures t-test, or a between subjects ANOVA and a repeated measures ANOVA. The key difference there is, are you having multiple data points for each person? Because that's repeated measures. So a repeated measures t-test would be what you'd use if I have people do some sort of test in the morning, and then I have those same people do a test in the afternoon, and I compare their morning versus their afternoon, but it's the same people. That would be repeated measures. But if they're different groups of people, it would be between subjects or independent samples. And so long as you're comparing 2 sample means, it's a t-test. You just got to figure out if it's between subjects or repeated measures from the question. If it's more than 2, then you're using an ANOVA. So pretty easy rule of thumb. T-test is for 2 means, ANOVA is for 2, or ANOVA is for 3 or more. The only exception would be factorial ANOVA. So for a factorial ANOVA, well, you would have more than 2 means, because you have multiple factors, and each factor, like if you have sex or gender as one factor, and whether a student's in honors or not in honors in another factor. So there's 2 factors, and each has 2 levels. So you have men who are in honors, men who are not in honors. You have women who are honors and women who are not in honors. That's a 2 by 2. So there'll probably be questions on the exam trying to see if you recognize how many factors there are in an ANOVA. Most of the time, if it's just asking a simple this sample mean versus this sample mean, that's a t-test. If it's a one factor, like sample A versus sample mean B versus sample mean C, then you have to ask, like, how many factors are going on here? So if it's, let's say I want to know if student athletes, if there are any specific student athlete teams that have a better GPA, and I say, let's compare the basketball team versus the tennis team versus the golf team, you should see, like, okay, we can rule out a t-test because that's more than 2 means. But if it's going to be an ANOVA, is it a normal ANOVA or is it a multi-factor ANOVA? This would be a well, it'd be a one factor, the example I just named, because it's just sport is the factor. It's golf versus basketball versus tennis. It would be a multi-factor ANOVA if I said, I want to look at tennis versus golf versus basketball, but also men's basketball versus women's basketball, men's tennis versus women's tennis, so on and so forth. So that's most of, I'd say that's like 1/3 to 2/3, a good chunk of what the exam is just matching which test goes with which situation. You kind of think of it as a reading comprehension type of thing. Like, read the research carefully and ask the right questions. How many sample means are in here? Or if there's no sample means and you want to know if there's a trend, like as self-esteem goes up, does GPA tend to go up too? That's not talking about the mean of one group versus the mean of another group. It's talking about a, a degree of coincidence between two variables. That's a correlation. But if you are seeing something about means, you want to ask the right questions. Is this repeated measures? Is this between subjects? That's one contrast. Is this going to be a t-test or an ANOVA? So that's a question of how many groups are there? How many sample means are you comparing? And if it is an ANOVA, how many factors? If it has one factor, then that's different from a multi-factor ANOVA. I guess I'm kind of switching back and forth between the chat and the video. So if I don't see your post in the chat, just maybe turn off the mic and let me know. I'm going to go ahead and look at the final again and see what else I can ramble about. And y'all definitely stop me if I'm saying something that's not clear. Right, you'll want to understand chi-square. I talk about chi-square in the chapters at a pretty zoomed out big picture level. Like, I think I do go over the calculations, but you're not going to have to do any calculations. You'll have to know things like when to use it for sure, and what does the p-value mean if it's above 0.05 or below 0.05? What does it mean if you reject the null hypothesis? What does the chi-square statistic represent? You'll recall from the chi-square chapter and video that when you assume the null hypothesis is true, you get expected category counts. These are the number of counts you would see in each category if there's no underrepresentation or overrepresentation, that everything's just proportional. Men are just as likely to be convicted as women. No skew in the data. You assume the null hypothesis is true, so you get the real data versus what the data would look like if the null hypothesis is true. And the chi-square statistic represents how far apart those things are. So if there's a big discrepancy between what the data should look like, then chi-square test statistics can be really big. If the data more or less look how you would expect it to look, then chi-square statistics is going to be small.
We don't have to know anything about alternative hypothesis, do we?
No. So this class and every class you'll take at the undergrad level focuses on null hypothesis significance testing. So the goal is to see whether you can reject the null hypothesis. So you never really directly ask how likely the alternative, you just indirectly say, well, I know the null can't be right, so ... So no, I guess you need to know, like, if I ask you the definition of a p-value and one of the potential answers is it's the probability of achieving the data when the alternative hypothesis is true. If you know what the alternative hypothesis is, then you'll know that that's not what the p-value means. Although if you know what the p-value means, you know that that's has nothing to do with the the alternative hypothesis. That was a good question. Statistical power. Is everybody read up on statistical power? Basically, it comes down to sample size and effect size. The bigger the sample size you have, the more statistical power you have. If the smaller your sample, the smaller your statistical power. And statistical power, if you don't remember, that's from way in the beginning. Statistical power is your ability to reject the null hypothesis when the null hypothesis is indeed false. An alternative way of putting that is statistical power is the probability that you'll be able to detect an effect if there really is an effect. So in a way, it's like saying your ability to, well, you never accept the alternative, you just reject the null. It's your ability to reject the null when you should reject the null, and it is wrong. So if the null hypothesis really is wrong, but you don't collect that big of a sample, you might not be able to reject it, even though you theoretically should have. That's why you want a big sample, so you have lots of statistical power. So statistical power breaks down into sample size, and then on the other side of the coin, you have effect size. If you're trying to detect a very small effect, even if it's real, so the null hypothesis is false, then you're going to need a huge sample size to have good statistical power, because a small effect is just hard to find because there's so much randomness in the data. A big effect, though, you don't need that big of a sample. Like if it's a night and day difference, then you really don't need that big of a sample. The example I used in the videos was on the one hand, a small effect size would be like if I have an hypothesis that drinking diet sodas leads to you on average being shorter compared to people who don't drink diet sodas. Supposing that's true, there's just so many other factors that affect how tall people are that you'd have to have like tens of thousands, maybe hundreds of thousands of data points to be able to detect that that's a real thing that occurs. On the other hand, if you have a theory that people are better at bowling when you have not sprayed them in the eyes with mace, you go to the bowling alley, you get your participants to bowl, and they're having a good time. You get their average score, and then you spray them all down in the eyes with mace. Their bowling scores are going to get a lot worse. A lot of them are probably just going to quit your study and not bowl. So their score is going to be at 0. It's going to be a big night and day difference. You don't need tens of thousands of bowlers to see that difference. You'll see it just real quick with maybe 10 people. Any other questions about statistical power? Flies on my computer. How do people feel about reading interaction chart? I forget the chapter it's in. Whatever factorial ANOVA is covered, there's a talk of main effects versus interactions. And if you look at some sample means or an interaction chart, sometimes there can be a main effect without an interaction, and sometimes there can be an interaction without a main effect.
What's a good example of that?
Let me think. It's hard to do that without just Googling and doing a Google image search. So like if you're doing a study, So an interaction means that the two factors, this is multi-factor ANOVA, is where you can see an interaction. So you have multiple factors. If there's an interaction, then the factors play out differently depending on which level of which factor you're on. But if there's no interaction, it means that the factors are independent. They don't affect each other. So that is perhaps not so easy to recall. So I'm going to try to, can I share my screen on this? Let me see. Mute, turn camera off, more actions. Enter full screen. God, this thing is annoying. Maybe I can drag some pictures into the chat. Let me see if I can do that. Then the people watching later won't be able to see. What's this? Hot dog, ice cream.
Go to open share screen.
What's that?
Right, go to open share screen right next to the mute.
There's an open share screen right next to the mute.
Mm-hmm.
The
menu
arrow.
bar.
I see open share tray.
Okay, there you go. That one, open share tray, and then on the bottom, it's going to open up where you can share a whiteboard or files, etc.
Let's see. Did that work? Can y'all see my screen?
Yep.
Awesome.
Yep.
Nice. Thank you for helping me figure that out. All right, so this is an interaction right here. I'm trying to figure out what this is. We got hot dog and ice cream and enjoy. Okay, so enjoyment is the dependent variable. This is how much you enjoy hot dogs versus how much you enjoy ice cream. And then we've got chocolate sauce and mustard as the toppings. Okay, yeah, I can definitely see an interaction here. So hot dog with chocolate sauce is not enjoyed too much, but hot dog with mustard is enjoyed a lot. So whether you enjoy a hot dog or not depends a lot on the condiment factor. And whether you enjoy ice cream or not depends a lot on the condiment factor. So the food factor has two levels, hot dog versus ice cream. And there's definitely it's not just the food that affects your overall enjoyment, it's the condiment too. And it's not just the condiment alone that affects how much you like something. Mustard doesn't just always make anything taste better. And not always make anything taste better. It depends on the food. That's really what's at the heart of an interaction, is that one factor, how it affects the dependent variable, is going to interact with the other factor. So there's definitely an interaction. These lines are not parallel, they intersect, which is a pretty decent definition of an interaction. If you want to know if there's a main effect of food, there's not, because if you take the average of hot dog, you've got like 65 and 90, meet in the middle. It's a little bit above 75. So going from hot dog to ice cream, the average of hot dog is around 75 if you disregard chocolate versus mustard. You go over to ice cream and it's about the same. It's like 94 versus 60 something, it's going to come out, you meet in the middle, the average of ice cream and the average of hot dog are basically the same. So there's not really a main effect of food type. It's not the case that people just like one ice cream or hot dog better than the other. There's also not a sense in which mustard just tastes inherently better than chocolate sauce, because if you meet in the middle, the chocolate sauce for hot dog and the chocolate sauce for ice cream, if you average those and meet in the middle, you're on top of the average of mustard on a hot dog and mustard on ice cream. So a main effect is when you take one factor and just ask, when I go from one level of the factor to the other, does the averaging across all the levels of the other factor result in a net gain or a net loss? Here it's staying the same. You average over food type, chocolate's not much better than mustard. They're about the same. You average over condiment, and hot dogs not much better than ice cream. So this is an example of no main effects, but definitely an interaction. And then over here, let me try and figure this out. Judge qualifications is the dependent variable. Okay, so they're judging how qualified someone is. Okay, they do studies. When you are hanging out like at a job interview, if you show up at a job interview with someone who is obese, the interviewers will think that you're less competent because of the company that you keep. It's one of those nasty little psychology things where we don't ignore things that we should ignore, and we make assumptions about people that we shouldn't. So the companion is either obese or typical. And what's the relationship between the companion and the person showing up? Are they just an acquaintance, or are they the person showing up girlfriend? If someone's showing up for an interview and they're like, hey, this is my acquaintance, or they're saying, hey, this is my girlfriend, and whoever it is that's with them is either obese or a typical weight. So this is a chart where there's main effects for both factors, but there's no interaction. So being obese, when you ignore whether it's an acquaintance or a girlfriend, so ignore the relationship factor and just average between those on obese, your judgment of how qualified you are, there's a net increase when you go from obese person with you to a typical person with you. Average between acquaintance and girlfriend up here versus down here. Moving from one level to the other on this factor, companion weight, there's a net gain in your perceived qualifications. Similarly, if you meet in the middle with when it's your girlfriend, it's you meet in the middle down here versus meet in the middle up here. So girlfriend versus acquaintance, there's a net difference when you average over the other factor. So there's a main effect for both factors, companion weight, obese versus typical, and whether the relationship you have with the person, whether it's just your acquaintance or whether it's your girlfriend, both of those things have a substantial effect on your qualifications, but there's no interaction. Whether the person's obese or typical that's with you has the effect that it has regardless of whether it's girlfriend or acquaintance. And whether it's your girlfriend or acquaintance has the effect it has regardless of whether they're obese or typical. Because these lines are basically parallel. There's no, they don't intersect, they don't meet at one point. Let's see. Where's a good example? Oh, here's another great example of this is an interaction. Let me zoom out. This one is food quality high and low versus parasitism, infected or uninfected. And the dependent variable is number of offspring. I'm not going to try too hard to figure out what the hell this is supposed to be about, but this first factor, high whatever, the mean is, you meet in the middle and it's about a 30-ish. And you can see these lines aren't parallel. You come over to the other factor, when you're low in food quality, the mean goes down. So you know there's a main effect of food quality, and you know there's a main effect of infected versus not infected, because if you meet in the middle for the teal bar and you meet in the middle for the orange bar, they're clearly far apart. But crucially, the teal bar for uninfected and the orange bar for infected, they get closer together. When food quality is high, they're far apart. When food quality is low, they get closer together. So they're not parallel. There is an interaction, meaning that the effect of one factor on number of offspring, or whatever this dependent variable is, the effect of one factor depends on which level of the other factor you're on. So hopefully that made some kind of sense. Let's see. Now I'm going to unshare just so I can go look at the final real quick. I know y'all would never screen cap the final, but I wouldn't be a very good teacher if I just live streamed the contents of the final exam. Pros and cons of between groups and repeated measures designs. Should I go over that? Does people feel comfortable with that? I want to apportion my time out to what needs to be gone over. I don't want to go over every single thing and be here for like 3 hours, but I'll just assume y'all want to talk about it. Pros and cons of between subjects and repeated measures just comes down to statistical power, we were talking about earlier. If you do a repeated measures design, you have more statistical power. So if I want to beg my department chair to have all of our stats classes in the afternoon and never have them in the morning, he'd want to see some data to support that. So I'd have to go on a year when I have them in the morning versus a year when I have them have students at in the late afternoon. That would be an independent samples between subjects design. So if there is a difference, I might not see it compared to if I did in the same semester. I had my morning class. I said, okay, I'm going to give you all a pop quiz. Then I want y'all to come back in the afternoon, same people, and do a different pop quiz. And I'm going to see if y'all do better or worse. That would be a repeated measures because it's multiple observations per person. And I'm more likely to be able to detect an effect. I'm more likely to be able to reject the null hypothesis when you use a repeated measures design. It's not important that you know why. I want you definitely to know that repeated measures means more statistical power. I will say the reason, just real brief if you're curious, the reason you have more statistical power is because the residual variance and the dependent variable that is not accounted for by your model can be reduced, can account for morning versus afternoon if it's independent samples t-test. If it's a repeated measures t-test, you can also say it's morning versus afternoon, and each individual person has their own subject level mean, so you can reduce the amount of variance left over that needs to be accounted for. But like I said, if that went over your head and you just want to prioritize passing the exam, that's not going to be on the exam. Not the reason why, but just the fact that you use a repeated measures design, you have more statistical power. That's the pro. The con with repeated measures designs is the chance that you'll have carryover effects. So if I do a repeated measures design and I have my stats students in the morning do a pop quiz in the morning, and then I have them come back in the afternoon and do another pop quiz, there's a chance that they kind of got their practice in the morning and they had to like kind of think about these things. And so when I have them come back in the afternoon, they might improve just because they practiced earlier in the morning. Anytime you do a repeated measures test, the data point they provide earlier in time might affect how they perform later in time. That's a carryover effect. And I personally, that's the reason I always avoid repeated measures designs in my studies, because I know you get more statistical power. And believe me, I'd love to have that statistical power, but I don't want to take the risk that anything I'm asking my participants to do over and over and over again, like I have you do basically a different version of the same task 20 times, someone might start to get lazy by the time they're on the 8th or 10th version of that task. They might say, okay, well, I'm going to start phoning it in because I want to get done with this study. I'd rather ask them to do it once and they do their best that one time, and I'll just have to get more people to do it because I don't want carryover effects. Any questions about pros and cons of between subjects versus repeated measures?
Can you go over the regression model situation? Because the whole last chapter has a lot of math in it.
Are you talking about the general linear model side?
Yes, and it says to review the regression model and everything else.
So I can go over regression and talk about like what it's for and what the intercept is and what the slope is. I'm happy to do that. There's also, I want to make sure I don't do that, but like what you really wanted to know is for the general linear model, which I think is chapter 9.
Yes.
That chapter is focusing less on what regression is and what the parameters mean. It focuses more on just revealing that regression and t-test and ANOVA are really all the same thing under the hood. So which one did you want me to go into?
Honestly, I've tried to read this a couple of times and there's just so much math. I guess whatever you think is important for us to know.
Okay. Well, I'll quickly go over the regression chapter and then I'll talk about chapter 9 in more depth.
Okay.
And if it's not working, I can go back.
Thanks.
So regression model is when you're trying to make predictions with a line. Like if you want to predict someone's GPA and you have other bits of information that you can use, like what's their gender? Are they in honors? How high is their self-esteem? What was the socioeconomic status of their parents? Did their parents go to college? Are they high in self-efficacy? Any information like an independent variable that you think could potentially improve your predictions about someone's GPA or whatever the dependent variable is. The dependent variable could be their level or severity of depression. It could be the severity of, or it could be the likelihood that they'll attempt suicide sometime in the future. It can be whatever. A regression line is just a line that where if you plug in any value for the independent variable, like if you say this person has a self-esteem of 20, now predict their GPA, or this person has a self-esteem of 35, now predict their GPA. For any X you plug into the equation, there's always some part of the line that will go along and correspond to that part. Am I screen sharing right now?
Yes.
Okay, thank you. Let's see. Simple linear regression. Let me find a good one. Unfortunately, other disciplines use regression. So like I'm seeing chemistry stuff, and we don't want to use that example. That's lame. What is this? Audience? Okay, this isn't too bad. This is kind of similar to what we did in the labs. Audience scores versus critics scores. So the critics, if they gave, I guess this is movies, I don't know. If the critics tended to give a certain score, can you use the critic score to predict the audience score? So if you feed pairs of this is what the critics thought of this movie and this is what the audience thought of this movie, you feed all of those pairs into your statistics program and say, I want to do a regression model where if I give you a critic score, you'll give me a predicted audience score. Then it'll shoot out a slope and an intercept such that when you plug a critic score in, it'll give you somewhere on this line, it'll give you its prediction for what the audience score was. So if you say, okay, well, you've made your regression equation, thank you, software. Now, if a new movie comes out and the critics gave it a 50, what's your prediction for what the audience is going to think? Well, you just come here to the 50 and you look at wherever this line is, it's around 58-ish. It's going to predict right where this line is. So it's just a way of making predictions. And the intercept, there's statistical tests done on the two parameters of a regression model. The two parameters are the intercept and the slope. And the statistical tests are determining whether there's enough evidence to conclude that these parameters are not actually equal to 0 in the population. So if the intercept is not equal to 0, that's not very interesting because in this chart, they don't even show 0 on the y-axis. So it's kind of trivial to say, yeah, well, the regression line probably crosses over the y-axis at a part that's not 0. Like, who cares? That's not very interesting. What is interesting is if the slope is not 0, because if the slope is 0, then it's flat. Knowing the critic score doesn't tell you anything about what the audience score is going to be. So that's what you're really interested in, is knowing whether the slope is positive or negative or just anything that's not 0. If that's statistically significant and you can reject the null hypothesis that the slope is 0, then you feel good and you can go publish your results and go buy yourself some ice cream or something. So that's regression. And one of the big reveals of this class is that really, technically, everything we've learned, except for chi-square and everything except for chi-square and Fisher's exact test. So t-test, ANOVA, correlation is all just some form or another of regression. Like if you go to a more math-heavy version of this same class that covers the same topics but focuses more on the math, you'll see that it all comes down to my predicted y equals intercept plus x. So let me pull up the chapter 9 chapter because that has some good illustrations, and I'll link this up to how is it going to be asked about on the exam. I could find, no, not chapter 8. Chapter 9. There's a chapter 10. Get out of here. When did I put a chapter 10 in here? So with a t-test, that's when you're comparing two sample means. you know, you got your control group, which is around like 140 something. You got your experimental group, the average is around 150 something. You do your statistical test and you predict, or you do your statistical test and you can conclude that these groups have a non-zero difference between them. You can reject the null hypothesis if p is less than 0.05. That's really the same thing if you took everything in the control group and said x equals 0 if you're in the control group and x equals 1 if you're in the experimental group, then if you did a regression model and just said, these are all of the people in the control group, their scores range from like 80 to 250, but most of them are right here around 140 something. And then in the experimental group, these are all they're over here all lined up on the 1 versus all lined up on the 0. They're all lined up on the 1. You know, it just forms 2 columns of data. And if you say, okay, I want to predict someone's score based off of whether they're in the control group or the experimental group. So if I draw a new person at random and I say, what do you think their score is going to be? You say, well, tell me whether they're in the control group or the experimental group. If they're in the control group, that's 0 right here. So my prediction is going to be right here, the mean of the control group. If it's in the experimental group, then I plug 1 into the regression equation and I say, well, my prediction is going to be the mean of the experimental group, which is up here. So the slope represents the difference between groups. And really at the end of the day, what that means is that if you were to do a t-test to test the difference between 2 means, or if you were going to do a regression and code which group someone's in as a x variable, and so the slope represents the difference between the groups, you get the exact same results. The p-value is the same, the t-value is the same, the degrees of freedom are the same, because fundamentally these are 2 sides of the same coin. You're doing a t-test or you're doing a regression. And if you do an ANOVA, that gets a little more complicated. I think I do try to explain it briefly in chapter 9, how with dummy variables. This is something you can worry more about when you go to grad school. But for now, just know it is possible to do an ANOVA with the regression and you get the exact same results. So in an exam, I might ask you a question like, look, I've got this research situation where I want to know if my magic pixie dust that Dr. Oz is trying to sell, if that indeed improves. What is oh yeah, weight loss is what Dr. Oz is always saying his stupid stuff can do. Dr. Oz says this new pixie dust, if you snort it, you'll lose weight. So I'm gonna say, okay, well, I'm gonna do a control group where there's pixie dust without the active ingredients, and then there's pixie dust with the active ingredients as my experimental group. My test question will say, okay, let's say I do a t-test on this experiment and to test the difference between the mean of how much weight loss you have for the control and the experimental group. Or let's say I do a regression equation and I want to know if I can reliably predict how much weight loss someone experiences based off of whether they were in the control group or the experimental group. The answers might be, well, you're more likely to get a significant effect in the t-test, or you're more likely to get a significant effect in the regression. The correct answer is going to be, it doesn't matter because they're the same thing. 2 different ways of getting the same result.
Thank you.
Yeah, absolutely. Where did It's still, I'm gonna go, and unless people want to stop, I'll probably go until about 9:30, unless everyone quits on me before that. I'll just keep, unless anyone has specific things they want to talk about. I'm glad someone brought that question. That was a good question. I'll just keep looking at what else is on the exam itself. So I talked earlier about the test statistic for chi-square. As chi-square gets bigger, what does that mean? And I explained that when chi-square gets bigger, that means there's a bigger distance between the actual data and the data you would expect to see if the null hypothesis is true. There are other test statistics like the t value or the f value. A t value represents how large a correlation is in absolute value, but weighted by sample size. So if you observe a huge correlation, but based off of only 10 observations, you're not going to get a very big t statistic. But if you observe that same correlation with many hundreds of observations, that t statistic will be very big, because the t statistic corresponds to the strength of the correlation, but taking into account how large the sample size is. Same thing with a t-test, the t's in the name. If there's, let's say, a difference between two sample means, like the control group and the experimental group are far apart, the t statistic will be large if they're far apart, but not if they're far apart and there's only like 3 people per group. So like 6 people total, 3 in the control group, 3 in the experimental group. T statistic's not going to be very big for that, even if the difference between the groups is large. But if you have hundreds of people per group and there is still a big difference between the groups, then the t statistic will be large. With the f statistic, which you might remember from ANOVA, the f statistic gets larger to the degree that there is some difference among the sample means. So remember, an ANOVA is used when you've got more than 2 sample means. You can compare tennis players versus basketball players with a t-test. But if you want to compare tennis players, golf players, basketball players, and football players, you're going to have to use an ANOVA. And when you do the overall ANOVA test, if you get a significant result, that only tells you that at least one of those sample means is different from the others. It might be the case that they're all different from each other, or it might be the case that 2 of the sports are higher than the other 2 sports, or that 3 of them are higher than the one. You don't know. But if the F value is high enough and that corresponds to a low P value, that just means that somewhere among the different sample means, there is a large enough difference that you can conclude that there's a significant, what they call an omnibus F test or omnibus ANOVA. You then have to go and do follow-up tests and test specific groups versus specific other groups. If no one has a question about that. Talking about is a perfectly fine question. A lot of these questions have to do with spotting, like, oh, that's a repeated measures t-test, or like, oh, that's a between subjects ANOVA, or that's a chi-square test, or that's a correlation. Just being able to match the scenario with the test. Pretty much everyone I'm looking at is that. There's one question about family-wise error rate, which is fitting because I was just talking about ANOVA. Does anybody remember why we do ANOVAs instead of just going and doing a bunch of t-tests? What did I use in the chapter? It was coffee versus monster versus no coffee for speed dating. That was a weird example. What's an exciting example I can use? The amount of sleep someone gets, depending on if they're what group? Depending on their profession. I don't know. That actually sounds kind of boring. Doctors versus lawyers versus teachers. Who gets the most sleep? I don't know. Unless y'all can suggest a better scenario, I'll just go with that. So if you have a group of doctors and lawyers and you want to know who on average gets more sleep or less sleep, you can test that with a t-test because you have two sample means. If you have doctors, lawyers, and teachers, and you want to know who on average gets more sleep or less sleep, you can't do a t-test because a t-test is only for two means. Someone might be tempted to say, okay, well, let's do one t-test on doctors versus lawyers, another t-test on doctors versus teachers, and then the last t-test on lawyers versus teachers. That way, every pair of the three has a contrast. So you'll know which ones are statistically significantly different from the others. The problem with that is there's such a thing called a family-wise error rate. When you conduct a statistical test, it's assumed that that was a planned test, and it's the one test that you're performing on your data. When you do that one test, the probability of committing a type 1 error is 0.05. But if you keep running extra tests on the same data, then the probability that you're going to perform or commit a type 1 error increases. So one very famous psychologist, he's disgraced now, or at least he is to me, is this guy Daryl Bem. Is he at Cornell or Yale? I can't remember. But he published a study that claimed to have evidence that there's such a thing as precognition, like seeing things from the future. And the way he did it was he collected data, he analyzed the data, and the data said, no, people can't see into the future. And Bem didn't take no for an answer. So he found new ways to analyze it, tried different tests, tried excluding some people and including others. Like only people who said they believe precognition is a thing are allowed in. Try analyzing it all different ways. That's equivalent to going and shooting dice and just eventually, even if you're not likely to win on any given round, if you play enough, you're eventually going to win. That's kind of what's going on with a family-wise error rate. You're rolling the dice enough that eventually you're just going to get a false positive. You're going to get a p-value that makes it look like you can reject the null hypothesis, but the null hypothesis actually was true. That's what a type 1 error is. So that's why you can't just keep doing all kinds of tests. We do an ANOVA because the ANOVA will say, okay, yes, there is somewhere in this data a legitimate difference between means. Now that you know that, you can go and perform your t-tests and whatnot. But to keep your error rate, your type 1 error rate at 0.05, not higher, you don't want it higher, then you have to do an ANOVA and not do a bunch of t-tests on everything. All right. That's more pattern matching for that one. Oh gosh, there's really one that just is interpret a p-value. Okay, know what a p-value is and how to interpret it. My judgment about what's an easy question and what's not might be skewed, though, as some of you might want to scream at me. Yeah, if you don't know, let's see, that's 17 I was looking at. If you don't know, when you do null hypothesis significance testing, this is all the way from chapter 1, module 1. If you have a hypothesis, like I think there's a relationship, a correlation between this variable and this other variable, the procedure that is commonly used at this level, like in your training, and probably for the rest of your training, if I'm being honest, is you don't test whether you're right, you test whether you're not wrong. So you form a null hypothesis that says you're wrong. So if you're testing a correlation, you say, like, I think there's a correlation between these variables, but suppose I'm wrong. If I were wrong, what's the probability that I would see data that are this correlated or more correlated? And if there's less than a 5% chance of observing that data, then you reject the null hypothesis and you conclude that you were right all along. So as basic as it might seem, maybe it's just because I've been teaching this stuff for so long, it's hard for me to, like, maybe people overthink these questions and that's why they still miss it. I don't know. You see a p less than 0.05, that means reject the null hypothesis. That means the researcher was right about their actual hypothesis. I think this stuff is tricky, but after talking to students after enough exams, I think sometimes they do overthink things. I don't want to tell you to underthink it. I don't want to push you in the opposite direction, but like if there's literally a question that says, I did this study and p is less than 0.05, what does this mean? And one of the choices is that means the null hypothesis is probably false. And the other questions, I mean, the other possible answers don't look any better, then, I mean, don't overthink it. Don't underthink it, though, either. See, there's a question directly about interactions. We talked about that, but we can talk more about it if you're not feeling comfortable. There's a question where you plug in numbers to a regression equation. So I give you a regression equation, intercept, slope, you plug in x and you get a predicted y. Just remember order of operations. You multiply and divide before you add and subtract. Let's see, number 14. I looked at that one already. Do we know repeated measures versus between subjects? I think we went over that pretty well. Yeah, I'd say I talked at least a little bit about everything that's on the final. Is there anything we talked about tonight that you don't feel confident about more? Ready to take the final right now? Oh, here we go. This really helped. I feel much better. Thank you. Oh, thank you for thanking me. It warms my heart. Yeah, I hope it helped. I try. Definitely do the practice questions. I think I'm pretty good. Ditto on the thanks. I think you covered just about everything. Okay. All right. Well, I'll hang out here for another 13 or so minutes unless everyone nopes out. If you want to look over anything and ask while you have the chance, I'll be here. And remember, the exam, you get 2 attempts. It's open Thursday, Friday, Saturday, and Sunday. So you have 4 days to do 2 attempts. Open note, open book, open this. When I upload this, you can open it up and rewatch it. Everyone should theoretically do pretty good. Thank you so much. This is a huge help. You're welcome. Awesome. Thanks. Good night. Good night to you. You're very welcome. I have to start telling jokes past the time. You're very welcome. I hope this helps. I wish you all the best of luck. Let's see, we got. No. Hope so. It did, and it will help even more when I rewatch this video. Yeah, videos are good because you can pause it and like write it down, think about it, and come back. You too. Have a great night. It was nice to sort of interact with some students. It's kind of a big bummer with online courses. This you just kind of put some stuff out into the void and you hope people read it and watch it. So it was nice to have a synchronous meeting. Well, I know I said I'd wait till 9:30, but since there's only one person left, did you have any questions? Because I might just shut it off and upload it. If not, okay. Cool. Well, I'll go ahead and adjourn the meeting and I'll upload this. And good luck on the exam and have a good night.